Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week. And this is going to be about something called frontogenesis. And it's, I don't even know why I do this sometimes. I tend to really like math. And I'm hoping that at least some of you find it as interesting as I do. I know a lot of you do not. The only thing I can tell you is that once we get past the equations in this video, then there will be a sensible explanation as to what those equations actually mean, okay? So if you don't like math, I apologize, and I don't do this every video. It's just that every once in a while, for whatever reason, I just think it's interesting. So let's delve into it here, and I've entitled this Never Put Up a Front, although in meteorology it happens all the time. All right, so let's go on ahead and talk about a couple of things here, frontogenesis and frontalysis. Frontogenesis means any process that strengthens the horizontal temperature gradient. So if you have point A and point B, and initially it's 40 degrees in one place and it's 50 degrees at the other place, and a few hours later it's now 30 and 60, then you have a greater amount of temperature contrast over the same distance. And so the temperature gradient has actually strengthened. And so that would be an example of frontogenesis. Now, also frontalysis refers to any process that weakens that gradient. So let's say it starts off at 40 and 60, and a couple hours later it's 45 and 55. So the gradient has decreased. There's not as much contrast, and so that would be an example of frontalysis. If the cold side of a front gets colder and the warm side of the front gets warmer, then the temperature gradient gets stronger, and we have frontogenesis. On the other hand, if the cold side of the front gets warmer and the warm side of the front gets cooler, then the temperature gradient gets weaker, and we have frontalysis, okay? And there are several processes that result in the strengthening or weakening of temperature gradients. Okay, so let's get into the math here, and we'll get out of it eventually, I promise. So let's call frontogenesis F, okay? Let's just make that the substitute variable for it. And there are a couple of different types of derivatives in calculus. You have a partial derivative, and then you have a total derivative. So if something is changing with respect to something else and there's more than one thing causing it, then the individual things that are causing it would be partial derivatives, and then when you add all those together, then you have a total derivative, the total change due to all those different processes. So frontogenesis can be defined as the partial derivative of the change in temperature, that's what theta is, with respect to x, okay? So temperature is changing along the x-axis, and we're looking at how that change is, or how that difference is changing over time. That's what that group of derivatives means. The change in time of the change in temperature over a given distance, okay? Now, you can also, there's a little bit of trickery in math that you can do where you can swap these variables here in the denominator, okay? So you can change it so that now it's the partial derivative with respect to x of the partial derivative of temperature with respect to time. So let's say that you have somebody at point A and the temperature in the morning is 30, and then the sun comes up and 3 or 4 hours later, it's up to 50. So d theta dt would be 20 degrees. It changed 20 degrees over 3 or 4 hours. And then we're looking at how that change is changing along the x-axis. Like maybe one place is cloudy and d theta dt is not that big, but at another place where it's sunny, it is. And so we're looking at how the local change at a given point is changing along the x-axis or along a certain distance, okay? All right, so notice, oh, and by the way, the total derivative of the change in temperature with respect to time is this term here plus this. This is what's called a dot product. It's the total wind dot product, the gradient in temperature. That's what that upside down triangle stands for. And that means advection. That means the wind is blowing a different temperature into your area, okay? So it's one thing to have the sun come out and heat you up. It's something else to have the wind blow a different temperature into your area. That's what that advection term means, okay? So let's get rid of that. Now notice that we have the same thing here, del theta dt and del theta dt. So if we solve this equation here for this, then we can substitute that into this equation up here, okay? So let's do that, if my remote control can work. There we go. So if you solve this equation here for del theta dt, this goes over to this side of the equation, this comes over to this side, so you have d theta dt minus the advection term. Okay, so the local change with respect to time minus the advection term. Okay, and then you can expand that out where you have the total wind, and the wind is made up of three components. The U component is west to east, the V component is south to north, and the W component is up. Okay, so you can expand this out, this advection term, to the U component times how the temperature is changing along the x-axis, plus the V component, the south-north component, how the times the temperature change over the y-axis, and then the up and down motion times how the temperature is changing in the vertical along the z-axis, okay? So this is just an expansion of this term right in here. Okay, then if you go back up to here, where it was the change in x, okay, the partial derivative with respect to x times that. Well, now we have that term here, okay? So now it is the change with respect to x of this entire mess, okay? The local derivative with respect to time, and then those three terms are the advection, okay? And so this is equal to that times that. All right. Now, if you expand that out, then you end up taking the derivative with respect to x times d theta dt, and then you have to go d dx times u d theta dx. In other words, this, you have to distribute this over all those terms to the right of it, okay? So you have to distribute that over this, over this, over this, and over that, and that's what all that is. Once that happens, then you start getting what we call a secondary derivative, okay? And we have three of those. You've got 1, 2, and 3. And it turns out that in meteorology on the large scale, you can ignore those second order derivatives. They're not that significant in terms of impact. So if you take those three things out, then here's what you're left with. The change, the frontogenesis change with respect to time, is the change with respect to x of d theta dt minus d theta dx du dx minus d theta dy dv dx and minus d theta dz dw dx. And each one of those terms means something different. It's a different process. So this is what we call the differential diabatic term. Now, what the heck is that? An adiabatic process is a process where there is no heat exchanged between the air parcel and the environment that it's in, okay? You can do that by compression or expansion. So when air sinks and the pressure goes up, then you're going to have compression and the temperature is going to warm. As it goes up, there's less pressure and it'll expand and get cooler, but there's been no net addition or subtraction of heat to the system. It's all been internal. Now, if you apply sunshine to an air parcel, okay, then that is an outside process. If you have condensation that releases heat, that's an outside process. If you have evaporation that causes cooling, that's an outside process. So that is a diabatic process as opposed to an adiabatic process, okay? That's what that term is there. These two terms I'm going to call confluence terms. In other words, is the wind coming together or is it spreading apart, okay? And we'll talk more about that in a second. And then this last term is called the tilting term, and this is where the vertical motion, the up and down motion, comes into play. So let's take these one by one. The diabatic term. Let's say that we have warm air here and cold air here, and we have the sun out over top of the warm air mass, okay? And so it's heating things up even more. It's already warm, but it's getting even warmer. Over here, it's raining. And let's say the air isn't completely saturated, and so you've got evaporation going on here, and this is getting even colder. So sun makes this warmer, rain makes this colder, temperature gradient is getting stronger. There's more temperature difference over the same distance, so the temperature gradient is strengthening. If the opposite were true, if it was raining here and the warm air was getting cooler, and the sun was out here and the cold air was getting warmer, then the temperature gradient would be getting less with time. And so that would be frontolysis, okay? All right, I forgot to add the ER there on both warm and cold. All right, so the temperature gradient is strengthening in this particular scenario. Now let's take a look at these confluence terms. So let's have three isotherms here, okay? These are lines of equal temperature. And we've got a northwest wind up here, so you're sort of looking down on the atmosphere. This is like looking at a weather map. Northwest wind up here, southwest wind down here. So these winds are going to blow these isotherms up like this, and these winds are going to blow that isotherm down there. And so the end result, holy cow, you know what's happening here? It looks like it's buffering. And I can't get it to go, oh, you know what? Okay, hold on just a second. I think I can get back here. Okay. Okay, we went through all of that. This is really amazing. Okay, so we start with our three isotherms. These arrows then tighten those isotherms. It pushes them closer together, and so you have a stronger horizontal temperature gradient, okay? You also have something called deformation. This is really interesting. But supposing you have isotherms like this, and then you have winds coming down like this from the north and spreading out like this, and then you have winds coming up from the south that spread out, and you have an axis of stretching right in here, okay? And so those winds are going to press that isotherm southward. These winds are going to press these isotherms northward, and the end result is they're going to be tighter, and you're going to have a stronger temperature gradient. And finally, the tilting term, that last term in the equation, looking now at the atmosphere in 3 dimensions. So supposing our isotherms are tilted like this, okay? And then you have upward motion here and downward motion here, and so the end result is that these isotherms then tilt into the vertical. So if you look at things along a horizontal line, there's not that much temperature contrast here, but over here now there is, because these isotherms have been tilted by the vertical motion field, okay? So usually in the atmosphere, we will get upward motion just to the south of where the maximum frontogenesis is going on. And in these kinds of situations, especially with snow, you can end up getting really heavy snow bands within a larger area of precipitation where amounts will be noticeably higher in that zone than they will be on either side of it. And so frontogenesis is something that is looked at, especially in winter storms, to try to figure out where these heavier bands of snow are going to set up. All right, I know that was a heck of a lot of stuff, and I hope at least one person found it interesting. I remember giving a talk out in Las Vegas one time, and there was some calculus in it, and somebody got in the elevator and he said, "You just made my day when you had that differential equation up there." And I'm sitting there going, well, you're as crazy as I am. At least I have a support group of one person. So anyway, okay, folks, that's it for now. I hope you have a great Friday evening, what's left of it, and even better weekend. We'll talk to you again on Monday. See ya.